The Nile Demo. This demonstration presents the design of STEAM, Purdue Boilermaker Stream Database System that allows for the processing of continuous queries over data streams. Specifically, the demonstration focuses on the query processing part, Nile. Nile extends the query processor engine of an object relational database management system to support data streams. Traditional SQL operators are extended to consider window execution as an approach to restrict the size of the stored state in the pipelined operators. In the following, we will show different applications that utilize the Nile query processor, and then we will visualize the internal processing of the Nile engine. Application 1. Traffic Monitoring. Moving cars on road network are continuously sending stream of data that contains the car identifiers along with the locations. In the traffic monitoring application, we have the road map of the Greater Lafayette City, Indiana, home of Purdue University. The objective is to discover dense traffic areas. On the map, we specify rectangular interstate regions, and then we specify the density threshold for that region. We also specify duration of time that indicates our interest over the history of the stream. In the example, the window is 2 seconds. When pressing the Submit button, the traffic monitoring application communicates with the Nile engine with a query that counts the number of cars in the specified area for the last 2 seconds. On the right bottom of the screen, the query result is continuously updated. Once the number of cars exceeds the specified threshold, the query result is plotted in red to alert for dense areas. More areas can be specified in this way, each with its own threshold. We keep track of the query results in the list at the right part of the screen. Notice that the query answer may increase or decrease. An increase in the query answer indicates that a new car had entered the interstate area. A decrease in the answer indicates that a certain car had moved out of the region, and hence a negative tuple is submitted through the query pipeline plan. Application 2. Retail Transaction. The retail application demonstrates the processing of two transaction streams, Stream 1 and Stream 2. Each stream consists of transactions coming from a set of different stores. Each transaction has the form store ID, item ID, price, quantity, and timestamp. The user monitors the streams by either choosing one of the 4 registered queries in the application or by submitting a SQL query. The screen is divided into 3 sections: the query section, the input section, and the output section. In the query section, the user submits a query to the Nile engine. In the input section, the input data streams are displayed. Stream 1 is on the left side and Stream 2 is on the right side. A relational table favorite items is displayed at the right part of the screen. In the output section, the output stream is displayed. Query 2. This query reports the total quantities of favorite items that are sold from Stream 2. The user can specify the window size using an input text field. The output stream consists of the item ID of the favorite item and the sum of the sold quantity. Its output record includes the timestamp. The chart area displays the most recent output tuples for the item specified in the field Display Chart for Item. For example, consider that the table of the favorite items contains items with identifier values from 10 to 29. By specifying a window of size 5 seconds and monitoring the item with identifier value 17, we can see the following. At time 0, item 17 appears with some quantity equals to 11. At time 1, item 17 appears again and the sum quantity increases to 47. At time 5, the first occurrence of item 17 expires, that is moves out of the sliding window. The Nile produces a negative tuple for the item 17, which is processed in the same way as the tuple 17 and results in a decrease of the quantity to the value 83. Similarly, at time 6, item 17 with quantity 36 and that first occurred at time 1 expires. Therefore, Nile generates a corresponding negative tuple for the item 17. Processing such negative tuple reduces the quantity to the value 47. We can terminate the query by clicking the Terminate button at the upper right corner of the screen. Query 3. This query reports the commonly sold items from streams 1 and 2, along with the sum of the two sold quantities and the selling stores. The window size parameter is entered by the user using an input text field. The output stream consists of the item identifier, the first store identifier, the second store identifier, the sum of the two quantities, and the output time for that record. The chart area displays the most recent output tuples for the item specified in the field Display Chart for Item. For example, consider a window of size 4 seconds and monitoring the item with value 6. We see that at time 1, item 6 occurs in stream 1 with quantity 28, but there are no other items to join with in the other stream. Later on, item 6 appears in stream 2 with quantity 47, which joins with the occurrence in stream 1 and produces an output tuple with total quantity 75. At time 5, the occurrences of item 6 at time 1 in both streams expire, which produces a negative tuple with quantity negative 75. At time 8, an occurrence of item 6 appears in stream 1 with quantity 20, which joins with the occurrence at time 6 in stream 2 and produces an output tuple with total quantity 61. Application 3. Video. In a medical video library, users may want to play back certain videos even if they do not have full access over the media contents. For example, the medical video may include some restricted objects such as the face of a patient. The enforcement of the access right of each user is molded as a continuous query executed over the medical video stream. The medical video is modeled in our system as a stream of consecutive image frames. Example 1. This example query represents a user playback request for a video with restricted parts. The continuous query blurs portions of the input medical video stream, which is locally stored on the Steam system in MPEG-1 format. The query is introduced using the input query interface. Then the query is submitted for execution at the back-end Steam system. The Steam system starts by decomposing the medical video into stream of frames using off-the-shelf video decoder. Then the stream of frames is pipelined in a query evaluation plan that includes two main operations. The first operation is a join that identifies the restricted frames by correlating them with a start trajectory of the restricted object. The object trajectory is a sequence of bounding boxes identified by the restricted frame numbers. The second operation in the evaluation plan is a user-defined projection. The projection function blurs video frames that result from the previous joining step. The final output video stream, as we see, has the specified face blurred while streaming the medical video. Example 2. As another example of continuous queries, we demonstrate a playback operation where the user wants to fast-forward the medical video stream. This scenario is similar to the previous continuous query, except for the fast-forward part. We implement fast-forward as a selection operation in the continuous query. The selection operation filters out all frames but the I frames. As before, We enter the new continuous query using the system interface and submit the query for execution on the server. The result of the query is a fast-forward playback of the medical video with the restricted object blurred. Visualization part. In this part of the demo, we visualize the Nile engine with particular focus on negative tuple processing. As an example, we show the execution of a query from the retail application. The query is shown at the right of the screen. Tuples are plotted in a blue color. Once a tuple becomes outside the window, a corresponding negative tuple is generated. Negative tuples are plotted in red color. A negative tuple goes through the same operators that its corresponding positive tuple went through and cancels its previous effect. The illustrated query performs a join between the retail stream and a start relation, and then applies the group by operation to the result of the join. At the bottom of the screen, we see input tuples entering the pipeline and then get processed by the join and the group by operations. As tuples expire, that is, slide out of the assigned window, negative tuples drawn in red are generated. Negative tuples follow the same steps as their corresponding positive tuples, in other words, get processed by the pipeline operators. We see the effect of positive and negative tuples on increasing and decreasing the values of the output stream respectively.